If ever I don't start the recording, somebody please interrupt me. I used to start my notes with, oh, here this one has, start the recording, because I'm sure one of these days I'm not going to do it. Okay, guys, so welcome to class, and we're moving along. We're in class 8, so we're more than half done. That's pretty exciting. And next week will be protein, and then we're going to spend 2 weeks on functional ingredients just because there's a lot of them. So let's see. So the learning objective for today is differentiate the types of fats and oils and lipids. And then it says functional and nutritional aspects. So we're going to look at that a little bit. I wrote a note at the bottom of this because I didn't like the way the learning objective was written, right? So it says fats, oils, and lipids, right? Well, fats and oils are lipids. It's not like there are 3 different categories, right? Fats and oils are lipids. So actually, the definition for lipid includes fats, waxes, sterols, which are like cholesterol, the fat-soluble vitamins, mono, di, and phospholipids. So those are lipids. So I didn't like the way that was written. So I just added a little bit. So just to clarify that. In general, we say that fats are solid at room temperature and oils are liquid. Oops. Oh dear.
That's why I only use fats.
Fats are solid at room temperature, right? And oils are liquid. We're going to talk a little bit about emulsions, the functional properties of fats, which I think you probably know. And then I'm going to give you some basic refining, some terminology. The ones that are listed here are the ones that you need to know. So winterization, fractionation, plasticizing, polymorphism, crystallization, and polymerization. Okay, so just looking at this is a table that I found, and I think most of you, did any of you have any questions about these? See, there's the functional properties. These are why we add fat, right? We have aeration, coating for crumbling and texture, flakiness, which would be a solid fat like in a pie crust, moisture retention, glazing, plasticity, which means makes it solid, and heat transfer. Anybody have any questions or comments on these? You want me to go through any of these in particular? No? I see John says no. No. Okay. These are all culinary things, right? So you should know these things pretty well. All right, good. So the physical properties, we'll go over some of those. So I think this is a little bit more, maybe a little more difficult. So the first one, the most important one, is melting point. So the melting point is the definition of that. Is the melting point is where it turns from a solid to a liquid. But it's a little mis I don't know, misguided or misleading when you say melting point, because actually fats have a melting range, which is dependent on the different fatty acids that are present there. So if it has a lot of saturated fatty acids, it's going to have a higher melting point. Sure it is. A higher melting point. Also, if it has a lot of long chain fatty acids. So we know that fatty acids can be from 18 to or up to 20 carbons long generally. So long chains. But if it is a bent If it has a lot of double bonds, then it's going to have a low melting point. So we think about a olive oil, for instance, or a vegetable oil. They have a lot of polyunsaturated fats. So while I'm not going to look too much at the chemistry right now, we're going to do this more in food science. This one right here is a saturated fatty acid. Saturated. Saturated means that there's a hydrogen for every carbon. So if you go along and you look at this up here and down here, there are hydrogens for every carbon. This is saturated. You cannot add any more hydrogen. And because it's saturated, it's a straight chain. And because just like when we talked about carbohydrates before, and we talked about amylose, and amylose being straight chain and forming a gel, this is the same thing that happens here. This is a straight chain, and these saturated fats can lay right on top of each other and make a nice solid, a plastic flat fat. So you think about Crisco, butter, lard, right? With a lot of saturated fat. But every time there's a double bond, so let's say you have an unsaturated fat, right? And we're looking at this one right here, an unsaturated fat. So there's unsaturated, see, there's two missing hydrogens. There could have been a hydrogen here and one here, but there are not. So there's two missing hydrogens. And every time there's a double bond, there's a bend in the fatty acid, right? So instead of laying like flat like this, they're more, they don't lay flat, right? So that if they don't lay flat, it's more liquid. It's not as dense. So the more polyunsaturated it is, the lower the melting point. Does that make sense? So things that have a lot of saturated fat. So let's look at beef right here, right? Has a really high melting point because it's saturated. These are all saturated. These are the names of the fatty acids. Fatty acids. And these are the food sources right here, the dietary sources. So foods that have a lot of stearic acid, which is found in beef and butter fat, have a high melting point and they're saturated. Foods that have a lot of, if the fatty acids with that are polyunsaturated or unsaturated, right? Like olives, we'll just do olives and avocados right here, have a low melting point. So what do I mean by melting point? If we have a thermometer and we have up here 158 degrees, we can say that we have to heat the saturated fats all the way up to 158 degrees before they go from a solid to an oil. Oil. But something with a low melting point, this one here, 61 degrees Fahrenheit, right? It has a low melting point. So it would be a liquid at room temperature. Because room temperature is 70, right? Comments, questions? Confusion?
Yeah, Joe, one question. You've got the beef and pork and different other beef and saturated fats, but farther down on the unsaturated fats, all the way on the farthest one, the arachidonic acid, what meat would fall into that other than beef, pork, chicken?
You're talking about down here?
Yeah, I'm trying to figure out what the other meat would be with those
Okay,
eggs.
so it's important to remember that all sources are a blend of of different fatty acids. So the ones that are solid are going to have a predominance of saturated fatty acid, but they will also have some polyunsaturated fatty acids in there, right? So
Okay,
there's
yeah,
always it's always a blend. It's always going to be, there's a, but it has to do with, well, with the physical property that we see, it has to do with the predominance. Which one is there most of?
okay.
Good question, John. Anybody else have a question? No? Okay, Greg's shaking his head. Helen's taking a nap. Sorry, Helen.
Taking a nap. It's just I have disruptive things happening here that no one needs to hear.
Oh, okay. I didn't really think you were.
Oh, my puppy is teenage, so it's not any, no one needs to hear that drama.
Oh, yeah. I know that. Yeah. Okay, so a couple other things that happen. A short chain fatty acid is going to be also going to make a difference. You know how long the chain is. So we look at these. All of these are 18 carbons long. And my neighbor's gardener decided to show up. How nice is that? There we go. Timing is excellent, right? So, right. So the length of the chain also is going to make a difference. So if we look at coconut milk, for instance, looking at this coconut milk right here, coconut is actually a solid. It's a saturated fat, but it's also liquid at room temperature because it has a short chain, the short chain fatty acid. This coconut is really short. But we'll talk about all of this stuff again when we talk about lipids in general. So most lipids are what we call triglycerides. So they have a glycerol molecule like this, and then they have a chain. Then we look at them like that. Okay, so like I said, it's the predominance. If there's mostly saturated fats, or if these saturated fats are on the outside of the molecule, then it's going to be a
Remember,
solid at room
there is
temperature.
never a reason to go vegan. Think of the animals.
Somebody's talking. Somebody talking to you, Trevor? No? Okay. So anyway, questions? So we'll talk more about this, but anyway, melting point is important. And I found this information in the essentials book, so you might want to go in there. I made a mess out of this. We'll erase some of this. There we go. Another physical property is what we call emulsions. So emulsions are liquid droplets stabilized in a layer of emulsifier and dispersed throughout a liquid or continuous phase. So they're two liquids that are immersible in each other. So an oil and a water or a vinegar, right? And so one is the droplets and one is the continuous phase. So if we look at an emulsion, what we see is if we look at this, my little drawing right here, right, the blue dots, the red dots around the outside here, and this tail, this is the emulsifier. So in this particular case, this is oil on the inside and water on the outside. Water on the outside. So the oil, right? So the emulsifier has one side of it that is water soluble and one side of it that's fat soluble. And so it makes a coating in between that coats the droplet. So in this pen, this is the tails. This is a diglyceride. So here's the tails right here. And the red dots are the water soluble part. So that's an emulsifier. So every emulsion has a continuous phase, a discontinuous phase or the dispersed phase, and an emulsifier. And emulsifiers come in the class of what's called surfactants or surface active agents. And so what surfactants are is they have a water soluble part and a fat soluble part. So they form the in between. So emulsifiers can include the natural emulsifiers like lecithin and casein, the synthetic emulsifiers, the mono and diglycerides, and the spans and tweens. Questions about an emulsion so far? They contain both a hydrophilic and a hydrophobic, or a lipophilic and a lipophobic parts. So in other words, that one part of them likes fat and one part likes water, and that's why they are able to keep the droplet. Do any of you guys use emulsifiers? John's going yes. And Trevor, yes. So do you know what the HLB number is for your emulsifier? Do
Nope.
you guys use that number?
Not without getting with my R&D people.
All right.
Which ones do you use?
I'm sorry?
Which emulsifiers do you use?
I
That's
use
another question
lecithin.
I'd have to ask my R&D team.
How about
I
you,
use
John?
lecithin.
Lecithin?
Yeah.
Yeah, so lecithin is in egg yolk, right? So
Yep.
when we make just standard mayonnaise, we use an egg yolk, but it can also be extracted, right? And so it can be an emulsifier, which why, Ben, sometimes people will take lecithin thinking it'll lower their blood cholesterol levels. Not. It gets digested and never gets into your blood. So it's digested just like every other fat and doesn't get into your blood and does not emulsify your blood.
I'll
So
cross that off the list.
yeah, chop that one off the list. You don't have to take that one. So we were just talking a little bit about nutrition and some misinformation, and that's one of them. So emulsifiers are characterized by their lipophilic balance. Lipophilic means fat loving balance, and it's called the HLB. And so it's a tendency to what how they work, whether whether the hydrophilic a hydrophobic balance. So anyway, so if you come across that term, that's really what that means. And oh dear, oh dear, oh dear, what did I do? I don't want to do that, whatever it was. Um, the oh, lecithin has a value of about 7, so it's neutral. It's about 7. So it's about right here. So this term here, this mono and diglycerides, these are what I've been terms I've been using. So I talked to you a little bit before about triglycerides, right? That most lipids are triglycerides. If it has only 2 fatty acids, it's a diglyceride. And if it has only 1 fatty acid, it's a monoglyceride. This part here is water soluble, and this part back here is fat soluble or fat loving. So that's why it's used like that. That's why the mono and diglycerides work. So they're nothing scary. They're things we eat all the time. Here's a picture of lecithin. So lecithin right here is kind of cool. So this is the fatty acid part. Remember, here's those chains. Here's the glycerol. The center right there is the glycerol. These are the fatty acids. This part right here is a phosphate molecule. So this part is water loving, and this part is fat loving. So that's why when you look at this picture, these pictures that I have right here, this is an oil in water. So you can see the tails on the inside here. They're the oil part, and the blue dots on the outside, they're the water. And this one here is a water with the blue dots on the inside and in oil. So there's 2 different kinds of emulsions, an oil in water and a water in oil emulsion, but the emulsifier is the same, right? Works the same way. So milk, cream, mayonnaise, and ice cream are oil in water. So they're tiny oil droplets dispersed in a continuous phase of water, while butter and margarine are water in oil. So the continuous phase is oil with little drops of water. So that's why they're not very stable. We know that. Questions? Okay. Factors that'll affect your emotion stability, which is much more what you're interested in than the rest of it. So if we add salt or acids, and if the emulsifier is a protein, they will denature the protein and it will no longer work as an emulsifier. So adding salt is going to bind some of the water and make it not available. Or adding acid will denature the protein. If we can capture some of the water, like we add a thickener, like for instance, a gum or a pectin or a gelatin, then we can get a thicker emulsion because we'll capture some of the water. Temperature changes, too hot, too cold will break the emulsion. And then violent shaking may also disrupt your emulsion. So there was a couple of questions in the discussion, I think from Laura. I think they came from Laura about emulsions, and I did an announcement, and in it included the standard of identity. So mayonnaise has a standard of identity from the government, and that standard of identity determines exactly what and what proportions of what goes into mayonnaise. So there are only certain ingredients, and it looked to me like they didn't include any gums, but I'm not sure of that. Because she's having trouble with her salads and the emulsion breaking. So I added some stuff to class.
So, Jill, for mayonnaise, having an acid added to it, what keeps that protein from denaturing if you're adding like acid and salt into mayonnaise?
Yeah, so that's a really good question. So obviously we are adding an acid because it's vinegar, right?
Mm,
And
vinegar, lemon juice, or malic.
yeah, and we're adding a table salt, right?
Mm-hmm.
Yeah, right. But the emulsifier is not a protein. The emulsifier is lecithin. And lecithin is not a protein. Lecithin is a fatty acid.
Gotcha.
Here, this is lecithin right here.
Mm-hmm.
So this lecithin is not a protein. It's a fatty acid, so it won't be affected.
So there's no protein from the egg?
Yeah, there is protein from the egg, and obviously if you got it too salty or too acidic, that protein would curdle or coagulate.
Mm-hmm.
Right. I suppose if you added too much, that might happen, or if you over handled it. But the amount of egg in there is so small.
Well, is that my question then? Is it that because the white has more protein, the yolk is more of the fat? So if you're just adding yolks, then
Right.
you're
Right.
not at risk of denaturing. Okay.
Right. Yeah, there is protein in the yolk, but most of the protein is in the white. So yeah, so you're not likely to denature them. I suppose you could if you worked at it hard enough, but they're pretty protected, I think. But if you had an emulsion and casein was the emulsifier, and I don't know, kind of an example of that.
Hollandaise.
Hollandaise, right? Yeah. So if casein was your emulsifier, the casein is from milk and dairy, right?
Mm-hmm.
So if that was your emulsifier, then adding too much acid could cause it to curdle. So you said hollandaise, right, Helen?
Yeah. It's confusing this one because both mayonnaise and hollandaise have those ingredients as really the main ingredients, and they emulsify really well.
Mm.
And not only do they emulsify really well, if they break, the re-emulsifier is more protein or more of the same ingredients again to fix it.
Yeah.
So maybe it's maybe it's, may reduce but not completely negate. That's a
Good.
tough one.
Yeah.
Because both of those examples are in high production.
Yeah. 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 Especially the mayonnaise part, right?
Hmm.
But commercial hollandaise, restaurant holidays, even restaurant hollandaise, where I've been anyway, this is made with a little bit of starch or something in there to cheat it so it doesn't break when it sits around. It always seemed to me that the hollandaise I make at home is much nicer. So yeah, so you'd have to look at your ingredients, and I agree with you. This is it is when I look at it really closely, it's a little confusing because
Hey, Jill,
obviously hollandaise is lemon juice and butter, right? And a little water,
and egg.
egg. Yeah. Oh yeah, that.
So we do a very nice hollandaise at Custom Culinary. First ingredient, heavy cream butter, lactic acid, whey protein, egg yolk. We do a lecithin as an emulsifier, but yeah, it's probably the closest commercially done hollandaise I've ever seen.
Uh-huh.
Right up there with the scratch kitchen hollandaise, but it's stabilized and unbreakable.
Does it have any gums or any or starches in it?
It does have a, guar gum, a xanthan as well.
Right. Okay. So all of those things. And then and also having the heavy cream, using heavy cream rather than butter, right? So
Well, the first three ingredients are water, heavy cream, and butter.
oh, okay. All right.
And even pure hollandaise with just a few ingredients made in a blender can go in and out of the fridge and be tempered again the next day. So it's pretty strong.
Yeah.
Yeah, it's
So this statement is really confusing.
yeah.
Well, let me do a little research then, and let me see what I wrote. And I got this out of the culinology text. So maybe it looks like I did, or out of a food technology. So I'll do a little research on this and see if I can clear it up a little bit, right?
Yeah, I mean, I think there is a traditional belief that things were a certain way, but over the decades, people have definitely challenged those boundaries, and it's totally proven that both of those items can be manhandled,
Yeah. Okay. And so
depending on how they're produced. Yeah.
yeah. Okay. Well, okay. That's really good. Um, so maybe I'm a little wrong. So I will look this up again and see if I can figure out what I did, right? What I wrote and see if I can clear it up. I will tell you that there's a mistake in the culinology books. This I know, all right? So the raw culinology text that it's mayonnaise is a water and oil, but it's not. It's an oil and water emulsion. So you want to find that in your textbook. And I think this article right here that I have right there also, I think that's probably where I got most of the information from, but I'll go back and look at it again. Moving on to something a little easier. We'll talk about emulsions again. So yeah, this comes and goes. Crystallization. So one of the things that fat does it'll form crystals, and depending on the temperature and the amount of agitation, the different kinds of crystals, like the beta prime and all those. So the smaller crystals are better for bakery items, I believe. And so the formation of crystallization. So fats will crystallize. And depending on what it is that you want it to do. And if they melt and recrystallize again, they'll get a different shape that won't be as functional as what it was before. Another thing is polymorphism. So this is many types of fat crystals can coexist in solid fats. So that's what I was saying. So they can, if you melt, they'll come back and will be a little bit different in a different shape. And that's called polymorphism. Polymorphism is the ability to form different kinds of crystals. We think about water crystallizes when it freezes, right? Well, those crystals are always the same, but depending on the placement of the fatty acids, and the temperature and the agitation, fats will crystallize in different ways, and that's called polymorphism. Plasticizing refers to the softening a hard fat, resulting in a change in consistency. Fractionization is the process of controlled cooling of the oil. So I always liken this one, fractionization, to if you put your olive oil in the refrigerator, right? So if you put your olive oil in the refrigerator, it gets all cloudy looking. So the more saturated fatty acids that are in there are going to crystallize, and that's what the cloudiness is. So if you were to separate those out, that would be a fractionization or fractionizing. So taking the different fats out depending on the percentage of saturation. So they can do that with a centrifuge. That's called fractionization. And winterizing is the same sort of thing, and all it's doing is removing the saturated fats. Polymerization is an interesting one. So that's overheating fats during frying. And so polymerization is the sticky gummy stuff that's on the outside of your fryer. Right? So overheating fats during frying, the fatty acids link together in long chains like this one right here. And they get really gummy and more viscous, and so that's the yucky gummy stuff on your pots that's almost impossible to get rid of. That's called polymerization. Interesterification is something that's really interesting. So, and I don't know how they do this, right? So if we have our fatty acid right here, our triglyceride, and you'll notice that this one is saturated on the outside and then polyunsaturated on these two. And this one is saturated, saturated, saturated. So what they can do is they can play musical chairs with these two and end up with a triglyceride that's saturated on the outside and polyunsaturated on the inside. And this one will have a higher melting point than this one, right? Higher melting point. It'd be more solid at room temperature. And I think that's how they make Crisco without trans fats, by what's called interesterification. It's musical chairs, right? So that's kind of neat. And that's one of the processing terms. So these other ones I think you're probably familiar with. Acrolein, which is the name of the smoke when you overheat your fats when you're cooking, and it's the burning greasing smell. Rancidity, when we in next class in food science, we're going to study oxidative rancidity and hydrolytic rancidity and talk about the difference. The smoke point is where your fat begins to smoke, and the flash point is the temperature that it ignites. Somebody asked me, how can fat burn? So it's the vapors will ignite in a flame. That's how fat burns. And has to be nice and hot, 600 degrees Fahrenheit.
Is the when we're talking about fat burning, is the fire point similar to the flash point?
Same thing,
Same thing?
same thing.
Okay. Because I had said fire point on the quiz and the correct answer was flash point.
Oh, because fire point is a word I made up.
No, it's an actual term.
Is it an actual term?
Yeah.
Oh, well, then I better change the quiz because I thought it was just it's called a distractor.
Okay.
Yeah, but it would be the same thing.
Actually, I should Google that.
Uh, I've never heard it called fire point before, but I wouldn't know. I wouldn't say not true. I just thought, distractors are very hard to make. This will be close, but not too close. So let me know what you find out. Saponification is making soap, right? The old time way of making soap where you took triglyceride and you add a salt. This one is baking soda, sodium hydroxide, and then you end up with salts of the carbolic acid in that soap. So some fun terms. So let's talk about something I'm more comfortable with. So let's talk about the dietary guidelines, right? So the dietary guidelines 2025 and have forever and ever said that saturated fat should account for less than 10% of our total calories starting at age 2 because the dietary guidelines start at age 2. That the acceptable macronutrient distribution range is 25 to 30% of total calories. So that's the recommendation. And that we should have a source of the 2 essential fatty acids, linoleic and linolenic. So linoleic, an omega-6, and linolenic, an omega-3 fatty acids. So those are the 2 essential fatty acids that we need in our diet. So that's the dietary guidelines. That's what they say. They also say we should limit cholesterol to less than 300 milligrams a day. The nutrition facts label is based on the dietary guidelines. And it is designed to encourage us to limit the amount of fat in our diet and the amount of saturated fat. So therefore, it has total fat, saturated, and then trans fat. So the limit for trans fat is 0 grams. And once they put that on the label, pretty much everybody has removed all the trans fat from their foods. And then cholesterol is listed on the label as well. And the reason for that, of course, is heart disease. Oops.
Which explains why everybody in our country is so fat and sick. It's
Because
all the nut oils and seed oils and vegetable oils.
yeah, right.
Yeah.
Yeah. We do like our fat, especially in our chips and things, the processed foods. So
I wouldn't know. I haven't eaten that in 3 years.
oh, good guy. Oh, wow, Trevor, good for you.
Yeah, 70 pounds lighter. I no longer need cholesterol medicine or high blood pressure medicine. I no longer
Wow.
have arthritis and I sleep like a baby.
Oh,
One
nice.
choice for us.
Yeah. But you know what? According to the guidelines, I'm unhealthy.
Oh, you're too thin? All right, we'll take it, right?
Yeah.
You know what it was, some old movie star said you can never be too thin or too rich. It's not quite true, but close. Okay, so anyway, so increased, so they put this on the label. This is the daily value over here, the daily value, right? So we talked about the daily value right there. So this is the daily value. So this particular food has 12% of our saturated fat of our total fat for the day and 23% of our saturated fat. And 12% of the cholesterol for the day. So this is kind of an animal product, since only animal products have cholesterol in them. So there's no cholesterol in plants. So anyway, so that's what that is. The daily value for fat is 78 grams would be the total daily value. So 78 grams, right, times 9, right? That would be how many of the 2,000 calories? Remember, this is based on a 2,000 calorie diet, right? And this would be 78 grams times 9.
702.
What?
I think 702, I think.
702. Thank you. So 702 calories, right? And 702 calories is 30% of 2,000. Yes, about 30%, right, of 2,000. So this would recommend 30% of a 2,000 calorie diet. So that's what the daily value is based on. And of that, 20 grams per day of saturated fat, and then 300 milligrams, and no trans fat. So that's what the label is based on. If you have a product that has less than 5 grams of fat per 0.5 grams, or a half a gram of fat per serving, and you could say that a teaspoon is 5 grams. So a half a teaspoon of fat per serving, it could be labeled as fat-free. If it has 3 grams or less, it can be labeled as low fat. You can also use the 25% or less from our regular product as a reduced fat. If you're having a meat product and it has less than 10 grams of fat or 4.5 grams of saturated fat and less than 95 milligrams of cholesterol, you could call it lean. And if it has less than 5 grams, you can call it extra lean, right? And I don't know why I put the calorie claims in here. Okay. Questions? So we have about 6 minutes left. So I just want to run through the fat replacers. Fat replacers have not been nearly as successful in the United States or in food manufacturing as the sugar replacements, that there are some around. So where you can do a fat replacer. There are some carbohydrate-derived fat replacers because fat adds mouthfeel and body to a food, right? So if you take the fat out, it gets watery and, not very tasty. So the carb, you can use a starch or a fruit puree like prunes, or a gum or a gel, and to add more body to your product, to give it a little, and we can use that as a fat replacer. There are some protein fat replacers. They because protein has 4 calories per gram, they do provide some calories, but not enough. In general, they so they might help. Simplace, modified whey. Protein concentrates can also be fat replacers. They can chemically alter the fatty acids. And that'll work as a fat replacer. So, but you know the one that got all the Olestra, that got all the press, right? The problem with these chemically altered ones is what goes in goes out, right? What they call that anal leakage is the way they described it. So, generally, you know, because it's heat stable, you could fry stuff in it, but it you know, it had a strange mouthfeel to it. I think it's off the market now. So any questions? That's all I have. I will look up the emulsifier thing and I'll make a note on that one. Okay. See, I always learn as much as you do.
Things are constantly changing in food.
Yeah, let me stop the recording.